Hello, 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 and welcome to episode 2 of I Want to Research It. This is the inaugural episode of the I Want to Research It screencast, and I want to welcome all of you. Just to give you a sense for what we're going to be doing on this show from episode to episode, is we're going to decide on a topic that we think is interesting, a question that we want to ask that we don't know the answer to, and we're going to look for the answer to that. And we're going to do it interactively. We're going to do it together. So, in most cases, the hosts, whether that's me or somebody else, won't know what the answer is to the question, and they're just going to dig right in and try to figure it out. Before I go any further, let me introduce myself. My name is Will Hawkins, and I'm a computer scientist. I live in Cincinnati, Ohio, in the United States. From time to time, I'll be joined by co-hosts and others from around the world who are interested and have insight to contribute to the question that we're trying to answer that day. Today, because I've done some pretty extensive research on this question before starting to record, it's just going to be me flying solo. So, what we're going to do, without further ado, is answer the question: how is it that the performance differs between a range or iterator for loop in Rust and a simple counter loop in Rust? So, without further delay, here we go. The question is, there are two different ways to write for loops in Rust, or to write a loop in Rust. One of those is the way that the documentation tells us to, which is to use an iterator. So what we're going to do is we're going to do that. We're going to write for, we don't really care what the variable is, so we're just going to say we're going to make it run a long, long time. And again, we don't really care what it's doing, and we don't really want it to do anything at all in the main loop. So let's just say we're going to iterate a variable here, or we're going to increment a variable. All right, and then inside here, we're going to do that. We're going to increment that by 1. And then, so that's one way to do a loop in Rust. Can't forget our in here, obviously. And we'll say that we'll take this down by 1 so we don't get any overflow. And that should do it. Good. Okay. Now, right now it's complaining about us. We've opened a mutable I here, but we don't modify it. So let's change that. We're going to do I is equal to 0. We're going to reset I. And then down here, we're going to use a similar loop. We're going to try to accomplish the same amount of work, except what we're going to do is we're going to write it using a while loop. All right. And we got to do that. Okay. So how does that look? Looks pretty good so far. Let's go over here and see whether we can compile it. Good. Compiles just fine. So let's run it and see what happens. Cargo run. All right, so it's taking a while. And I don't know if you can hear this, but in the background, my fan is heating up on my laptop here. We're very low fidelity on this show, so we just working alone here. Got a laptop. And so far what I found is I don't really like this. This is taking way too long to not do any work. This is very, very interesting to me. So let's try to figure out exactly how long this loop is taking. What do you say? So here's what we're going to do. First of all, for the purposes of exposition, we're going to turn this down by a few. so that it runs in a reasonable amount of time. I want to make sure that we're doing the same in both here. That would be an embarrassing error. And now let's go back over here and see what happens. Okay, good. So that's better. Runs faster. Let's add one more back in there so that's a little more appreciable runtime. Good. Now, we want to know whether the first loop runs faster than the second loop. How are we going to do that? Well, benchmarking is hard, but let's start with something simple. Let's try to get the difference. Let's take the time before the loop and the time after the loop. In both cases, we'll subtract the differences and then we'll compare the two answers. So let's do let mute before equals system time now. And let's do after about that. And then we'll say let, let's say iterator while iterator loop. Let's rename it this way so we can read it a little bit. Loop iterator equals before. What are we going to do? We're going to do after minus before. Good. All right. So let's see. Can we not do that? Well, apparently we can't. So I've got all this saved in a backup here. Let's do this. And let's see. Yes, this is what we want right here. We want duration since. This is a method on system time. And we're able to use that. So let's see. Duration since before. We'll change this to before, and all right, now we're good. Now that's happy. So let's do the same thing down here. And we're going to say we're going to call this type of loop a counter, just a simple counter, and we'll say counter iterator. We can't do this twice, so we're just going to do this again. How about that? And all right. So now we have a loop iterator and a counter iterator, and we're going to want to print this out. So let's just print it out to the screen so we can see this. And we're going to say we're going to print the counter iterator first. And then we're going to do this second. Because we're using debug here to print this out, there's going to be an OK wrapped around it, but that's okay. We can still figure out what's going on. So we'll say loop iterator loop counter. All right. Well, maybe not. We'll do loop. We'll do counter iterator and counter. That's better. Okay, now let's run this again, see what happens. All right, so what do we notice here? Well, we notice that the range or the iterator-based for loop, which is the first thing that's output, takes significantly longer to run than the second one. All right, that's very interesting. That's surprising. We wouldn't want that behavior in a program where we're following the Rust guidelines and we're trying to do the right thing. We don't want that to happen because, again, following best practices, all of a sudden my code takes a lot longer. When in reality, if that really were the performance difference, I would just opt to write for something as stupid as this and as unreadable as this, quite frankly, and then get the result that I want, the performance benefit. But before we jump too much further into this, let's actually figure out what's going on here. So we compiled this with debugging information on. So that means that in the target directory, the binary is in the debug folder, and it's here called episode 2. So let's look at the actual code that's generated. We're going to do objdump to do that, and we're going to do -d, which means to disassemble, and then we're going to do --demangle, which makes it readable, which demangles all the symbols and makes them readable. We'll see where that comes in a second. And then we'll say episode 2, and we're going to output it to a file called episode2.obj. All right, so now let's open episode2.obj and see what happens. All right, so a bunch of stuff that we don't really care about. These are all the libraries, and if you are familiar with objdump at all, or how the linker and loader works, all programs will bootstrap and start at the _start method and then go from there. So what we see is that we go through start, and then ultimately what we do is we call the main function. So let's jump to main, and here we are in main. The problem is we don't do any meaningful work in main that's Rust related or related to the code that we wrote. That actually happens in episode 2:main, main. So let's jump up there. And here we are. Good. All right. So now let's get down to it and see what happens. Looks like what we're doing here is we're going to make some space on the top of the stack. Now that we've called this function for all of our local variables, we're going to load effective address, which is what LEA stands for. We're going to load effective address of the function system time now. And then what we're going to do is call system time now. So if we were using Godbolt or something like that, or to try to watch these in parallel, what you would see is that roughly this is where we are right now. We're here in the source code, and that compares to roughly here in the assembly code. Then what do we do next? Well, we call that function, and what we're doing here is we're moving the result out of that function and saving it into a local variable. Now, what we notice here is that it looks like we're going to move this long hexadecimal number, and we're going to put it on the stack somewhere. What is that number exactly? Well, let's find out. So how are we going to do that? We're going to copy it, and then we're going to run it, and we're going to run GDB. It's my favorite way to print hex numbers. We're going to do that, and there you go. So there's our constant loop number of times from over here. You can see back over here that it's our loop number of times, just encoded in hexadecimal format. So now we're aware, we know that we're loading that on the stack. The stack pointer here is RSP. And it's going to be at offset 7C from the stack pointer. So whenever we see 7C offset RSP, what we know is that we're referencing the variable over here that's doing our loop counter. All right, very cool. So now what happens? We're going to go down here, and oh, it looks like this. This is interesting. It's going to take this variable from the stack, this 7C, which again is up here. It's our big 1 million number, or whatever it is, 100,000, 1 million, something like that, and pull it back into this register ESI. And if you're familiar with the ABI on Linux, EDI and ESI are two of the registers that are used to pass parameters to functions. So what it's saying is, I'm going to call this function that's coming up next with these parameters to it. One of which is the 1 that we passed at the beginning of it, 078, and the other is this 1 million number that we have here. So what you can see is we put 1 on the stack as well at the offset 78, hexadecimal 78, and we put this 1 million number on the stack as well at the offset 7C. And then what we do is we're going to load those down here into registers. Now that they're in the registers, those are going to be parameters to our function call. And down here, what we're going to do is we're going to turn that into an iterator. So again, roughly where we are in the code is right here in this area. All right, very cool. Now what we're going to do is after that function call, we're going to return back here where my cursor is. And we're going to take the results of that function and we're going to store them. The result of a function in the calling conventions in Linux are always in the AX, EAX, or RAX register. And so what we're going to do is put those on the stack at 0x60 offset. Very cool. What we're going to do a lot more work on that, yada, yada, yada. We're going to move some things around in registers. But now, here's the real meat of it. This is really, really interesting. Here's what we're going to do. We're going to actually call this function, this range next. And what that's going to do is that's going to get the next, that's asking our range to give me the next value out of it. That's really, really interesting and really telling. What it's telling us is that for each iteration of the loop, this has to be called over and over and over again. Now, let's compare that with what we see down here, which is the second version of the loop. And we'll be able to see that here. What we're going to see is, let's find the next call to the system now. Where are we here? We're going to call system now right here. So we're going to load the effective address of the system now function call. So we're going to call RAX. We're going to call through RAX, which is the address of system now, which means that we're going to be calling system now again. So now to get our bearings, let's find where that is here. So here's our second system now function. And so this is where we are. We're roughly on line 21. All right, excellent. Now, what do we need to do? We need to figure out where's the other end of this? Where are we bookmarking this? Well, we know that this is in RAX, so let's see if we can find another call through RAX and figure out where that is. Let's see, where are you? We're going to load this into RAX. We're going to call this, and down here. That's interesting. I can't seem to find the other one, the other call. Very interesting. So I wonder where you are. Let's see. Did we miss it? No, we did it right. So let's see up here if we've missed it. Where's our other call? I know we got to call it twice. So let's figure this out. Loop. Interesting. Well, I don't see it. Fascinating. What we can see here, though, is that we're incrementing EAX, and what this is saying is that this is where we're going to be doing our plus equal 1 down here, right here. So this is roughly on line 23. So this gives us a sense for our bearings, and then we're going to compare that with the top level value, and we're going to jump if that's not equal to 0. So let's see, where's 5DEE? And that's going to be out of the loop, probably down here. Interesting. Very interesting. So let's try to figure this out. Where are we here? So we call through RAX. So this is our first one. Oh, shoot. I seem to have missed this. So this is the bookend to the second one. I'm sorry. This is the second one here. The second duration now. The second system now. This is the bookend. So we're actually, when we're looking at this, we're up here. Interesting. Okay. So totally biffed that one. But good, we figured that out. So now, to get our bearings, let's find the second call. And we know that you're here somewhere, so let's see, where is that? So it must be right here. This is really interesting. Yep, it's right here. This is exactly what it's doing right here. So our function, our system time function before, our system now function, was being called indirectly through a register up here. We're loading the address of the function into the register, RAX, and then we're calling through that address and jumping there indirectly. Down here, what we're doing is we're actually going to call that by invoking it, by reading its position directly out of memory with respect to the register instruction pointer, where we currently are executing. So this is where we are here, is over here at line 21. So 5C64 is roughly equivalent to line 21 over here. And now we know we're in the middle of this loop, so let's see what happens here when we do this. We're going to do some addition here, and we're going to say, oh, interesting. Let's see if 989680, again, this is 1 million, and we're going to compare whether the value on the stack at offset 64 is less than that. That's a compare less than. And if it is, we're going to jump. And where we're going to jump, we're we're going to jump to 5C-A4. And where is 5C-A4? Let's see. It's down here. 4. And, okay, we're going to increment EAX. We're going to test. We're going to move. We're going to jump to 5E. So here's what we're going to do here. This is all Rust trying to detect whether or not we have overflow in that. This is more of that, more of that, more of that. And then we're going to be, at some point we missed our jump back. So let's see, where do we jump back? 5C-8-8. And we jump back to our comparison up here. And we jump back down here. Good. So I think we understand what's going on. The difference is that in the first one, we're actually invoking a function every time to be able to get the next value of our iterator and determine whether we're still within the bounds of the loop and determine whether to loop again. But what we want to know is whether or not the loop, how much that's actually costing us in performance. And we saw it's actually costing us a lot of time. Now, you're probably asking, well, that's all fine and good, but you're actually running that on with debugging on instead of running it with in release mode. Very good point. So now let's compare. So let's do cargo build release. All right. So now we have our release version. We're going to run target release episode 2. Okay. Now we're getting somewhere. That is much, much faster. And presumably, all that overhead of calling the range, or calling the iterator, and asking for it has been taken away. And let's guarantee that that's the case. So let's go back into target, release, and let's do jump, emangle, so 2.obj. Okay, and we're going to do episode 2.obj. Okay, going to do episode 2 main. Here we are. Oh, interesting. So now what do we see? Well, we don't see any calls to range-based loops. They're all gone. So that's really impressive. Really, really, really impressive. So that's where we got our speed up from. But here's the question. The question is, if you look carefully at this, and I cheated because I already did this once, if you look carefully, what you'll notice is there's no jumps in here either. And without any jumps, I really, really, really can't be doing any looping work now, can I? So, what does this make me think? Well, this makes me think that the optimizer has actually completely removed the loop entirely, which it has, because no work was being done. No meaningful work was being done. But that leaves us with another interesting question, right? And that question is, and I see that the iterator-based loop takes exactly, not exactly, but takes roughly twice the amount of time. That's really bizarre, right? So what's the problem? If the loops are optimized away in both cases, why am I still seeing a performance penalty? Let's try to figure this out. First of all, let's take the easy chance And maybe something screwy is happening because of the order of the program. All right, so let's play with that first. Let's take this whole loop and move it up here. And let's take this loop and move it down here. Okay, so now we've effectively reversed the two loops so that the counter-based loop is coming first and the range-based one and the iterator-based one is coming second. I realize that I named these variables wrong. This is very, this should be loop counter. I'm going to say, whoops, loop counter down here. Good. That's much better. Now it reads like a real program. And let's do cargo build release. Good. And now let's run it again and see what happens. Interesting. Very interesting. So now what you see is that the iterator version runs twice as fast as the counter version. But before, what we had was the exact opposite. And the only thing that changed was the order in which we did the two different loops. Very telling. So what that means to me is that there's something funky going on with the first call to system time and how long it takes. This is likely due to instruction cache misses on my CPU. And what we're going to do is try to figure those out and not optimize those out, but we're going to try to control for those by calling system time now before we do it for real. So we're going to do this, and then just to be symmetric, we're going to do this up here, and then we'll do that. Good. So now it's going to warn us because we assigned these variables but we never read them. So let's turn that off. Let's see, I figured this out before. It's over here, unused assignments. Unused, oh there it is. That's nice. I didn't realize that was going to happen. All right, unused assignments. So now we've got this. So what we're doing here is we're going to try to warm up the instruction cache on the system for the code through system time now, by calling it twice beforehand. We really probably don't need to call it twice. Once is probably enough, but we'll do it twice just because if one's good, two's better. Let's see what happens. Don't forget to build again. That's good. All right. It's exactly what we expected. That is the cause of the performance differences. Whew. We managed to figure it out. This is really good news. At least I think it is. But then again, I'm the one trying to figure this out, and you're watching along. So I hope you're as excited as I am. Great. So now we've got this figured out, and we've got two loops, and we know that our timing is consistent. So we've got a platform now where we know that everything is normalized, and we can really start getting down to actually measuring the performance of these loops once they're optimized away. But the problem is, again, I just said it, these loops are optimized away. So we need some way to bring it back. We need some way to make it so that the compiler, when it's optimizing, realizes that there's meaningful work actually being done in there, and it can't take it away. The answer to that is to use a crate called volatile. And the volatile crate does some nice rusty things under the cover and makes sure that it tells the compiler, hey, I'm going to tell you to do a read and a write to this variable, and you can't do anything with it. You can't optimize it away. It must happen. There's a lot of good reason for this. It's not just for benchmarking, why this is important, but it's still a pretty cool use of this crate. So I encourage you, you can look up the crate using the code that we're going to publish for this episode, and look at that if you're interested. The implementation is actually really interesting, and I encourage you to look at it. Maybe we'll come back to that in a future video, but I don't want to get too bogged down in that right now, because I feel like this has already gone on much longer than you are interested in following. So let's copy some code from what we already have over here. And we're going to do this. Whoops. Put this up here. Okay. So now what we're doing here is we're going to say that this variable j, I'm going to be able to read and write it through this volatile reference, this volatile wrapper. And when I do an operation through that volatile wrapper, the compiler cannot get rid of it. It must do it. It must do it. So how do we do that read and write? Well, we do this. And so that means that we're going to read the value that's currently in J, and we're going to add 1 to it. And then we're going to write that new updated value back to it. So we're doing the same thing as this, except we're doing it through the volatile. And much like we reset I here, although we didn't really need to, in the case of the loop, what we're going to do is we're going to do the equivalent and reset this. We're going to reset our V, which is J. And we're going to say write 0. So that makes us back to 0. And then we're going to put this down here. Boom. Good. All right, excellent. So now let's see what happens if we compile this and we run it. Good. So now we see that we're actually doing some meaningful work here. Excellent. Now, we're still getting this, we're still seeing that this is very interesting because we're still seeing some performance disconnect here. Very interesting. Let's look a little bit deeper at what's going on here and see if we can figure this out. So let's do this. First of all, let's take that away, since we don't need that down here, and see what happens. Interesting. Now, the good news is that in this make file that we've provided for this episode, what we've got is the ability to make a CSV file out of this so that we can run this a bunch of different times and see if there's any difference here. So now that we're running this faster, let's turn this up a little bit and make it loop longer. See what happens. Very, very interesting. So we're still seeing significant performance difference between the iterator version. It's actually faster than the counter version. So here's what I'm going to do. I'm going to do the old cooking recipe thing here, the old cooking show trick, and I'm going to copy over the code that I've built and published on GitHub into this file, and then we'll look at it that way. Cool. Like I said, this is all published on GitHub and is commented for your easy perusing. And here's what we're going to do next. We're going to run this make CSV. This is also provided in the make file. What this is going to do is produce a CSV file with a bunch of different runs, and we're going to be able to look at this in a graph and see what we see. No, we're not. We're going to do it up here. That's better. We're going to run this program 25 times, and that'll give us 25 different data points that we can use to analyze and see what the performance implications are here. Sorry for the delay. I think this will be worthwhile though. You can hear my fan heating up in the background. If only we had better production value, we'd probably speed this process up so that you didn't have to watch and wait. But we don't, and we're done. So let's see what happens when we open this file and graph it and see if we're going to be surprised here. Looks like exactly as I had suspected. So let's make a little line chart out of this and see if we can visualize what's going on here. Exactly what I expected. The performance of the two is almost identical. There's some noise, but if you look, they're roughly, if you squint and blur your eyes, what you'll see is that they're roughly equivalent. Now, what's the moral of the story now that we've gotten to the bottom of this situation? The moral of the story is that in debug mode, every time the loop goes through an iteration, in a iterator-based loop, it asks the iterator for the next value, which takes a significant amount of time because each one of those is then a function call. And if you compare that to down here, what we would be doing is just incrementing the value in a register in memory, depending on the optimization. That's a whole lot faster. But once the optimizer kicks in, this function call goes away every time through the loop, and the two loops become absolutely equivalent. And what we see then is, from a performance perspective, they become exactly the same. So the bottom line is, we do want to follow Rust's documentation guidelines, and we do want to write this loop using a simple iterator, because it is, as they say, much more readable than this loop, and it just looks nicer. It just takes advantage of everything Rusty about the world. So that's it for episode 1, which was actually episode 2, if you're following along at home, of the I Want to Research It screencast. I was your host, Will Hawkins. From time to time, like I said, we'll be joined by others who will be co-hosting with me. when they have expertise and interest in the topic that we're discussing. For now, if you have questions, please leave them in the comments section and we'll answer them as quickly as we can. Otherwise, check out the material online at our GitHub page, which you can find from our website. And